Did you know that the calming sight of clouds can gently lull you into a deep and restorative sleep? Welcome to our sleep story, Dreamy Cloudscapes, a soothing sleep meditation for ultimate relaxation, where we'll take you on a journey through serene skies filled with clouds, letting your mind unwind and your body relax as you drift off into a peaceful slumber. Clouds are visible collections of water droplets or ice crystals suspended in the Earth's atmosphere, formed through complex physical processes. They are a critical component of the Earth's weather system and climate, as they influence the amount of sunlight reaching the Earth's surface and help regulate the planet's temperature. The process of cloud formation begins with the presence of water vapor in the atmosphere. Water vapor is the gaseous form of water, produced through the process of evaporation from bodies of water, such as oceans, lakes, and rivers, as well as transpiration from plants. As warm, moist air rises, it cools due to the decrease in atmospheric pressure at higher altitudes. Once the air reaches its dew point, which is the temperature at which it becomes saturated, the water vapor in the air condenses into tiny water droplets or ice crystals, depending on the temperature and altitude. These tiny water droplets or ice crystals then come together and form visible clouds. This process of condensation is facilitated by the presence of condensation nuclei, which are tiny particles such as dust, pollen, and smoke that provide a surface for the water vapor to condense onto. The specific appearance, structure, and altitude of a cloud depend on various factors, including temperature, humidity, atmospheric pressure, and the presence of condensation nuclei. Clouds can vary greatly in size, shape, and color, and they can range from thin, wispy formations to towering, imposing structures. They can appear white, gray, or even pinkish-orange, depending on the angle and intensity of sunlight they receive, as well as the size and density of the water droplets or ice crystals within them. Clouds can also move and change shape rapidly due to variations in wind patterns, temperature, and atmospheric pressure. In addition to their role in regulating Earth's temperature, clouds also play a crucial role in the water cycle, as they are the primary mechanism for transporting water from one location to another. When cloud particles grow large enough, they can combine and form precipitation, such as rain, snow, sleet, or hail, which then falls to the Earth's surface and replenishes bodies of water. In summary, clouds are visible collections of water droplets or ice crystals suspended in the Earth's atmosphere, formed through the condensation of water vapor. They play a crucial role in the Earth's weather and climate systems, as well as the water cycle, and can display a wide range of shapes, sizes, and colors. The formation of clouds is a complex process involving the cooling of moist air and the condensation of water vapor into tiny droplets or ice crystals. This process occurs within the Earth's atmosphere and is influenced by factors such as temperature, humidity, atmospheric pressure, and the presence of condensation nuclei. Cooling of moist air. The process begins when warm, moist air rises from the Earth's surface. This can occur due to solar heating, which causes the air near the surface to become less dense and rise, or through the convergence of air masses, such as along weather fronts or over mountain ranges. As the moist air rises, it expands and cools due to the decrease in atmospheric pressure at higher altitudes. The rate at which the air cools is called the lapse rate, which can vary depending on the moisture content and other properties of the air. Reaching saturation. As the air cools, its capacity to hold water vapor decreases, and eventually it reaches the point of saturation. The temperature at which the air becomes saturated and can no longer hold all of its water vapor is known as the dew point. when the air temperature drops below the dew point, the excess water vapor begins to condense. Condensation process. Condensation is the process by which water vapor changes from its gaseous state to liquid or solid form. This transition requires the presence of condensation nuclei, which are tiny particles such as dust, pollen, or smoke that provide a surface for the water vapor to condense onto. When the air temperature is above freezing, the water vapor condenses into tiny liquid droplets, while at temperatures below freezing, it forms ice crystals. Formation of cloud particles. The condensation of water vapor onto condensation nuclei results in the formation of microscopic cloud particles. These particles can be as small as 1 micrometer in diameter or even smaller. As more water vapor condenses onto these particles, they grow in size and become visible as clouds. The specific characteristics of a cloud, such as its shape, size, and density, depend on the temperature, humidity, and atmospheric pressure at the altitude where the cloud forms. Growth and development. Over time, cloud particles can collide and coalesce, leading to the growth and development of the cloud. The interactions between cloud particles are influenced by factors such as turbulence, updrafts, and downdrafts within the cloud, as well as the size and distribution of the particles. When cloud particles grow large enough, they can combine to form precipitation, such as rain, snow, sleet, or hail, which falls to the Earth's surface. In summary, clouds form when moist air cools and reaches saturation, causing water vapor to condense into tiny droplets or ice crystals. This process involves the cooling of moist air, the condensation of water vapor, and the growth and development of cloud particles, all of which are influenced by factors such as temperature, humidity, atmospheric pressure, and the presence of condensation nuclei. Cloud seeding is a weather modification technique that aims to encourage rainfall by artificially stimulating cloud formation and growth. It involves the dispersal of substances, known as cloud seeding agents, into the atmosphere to create additional condensation nuclei or to alter the microphysical properties of existing clouds. The goal is to promote the formation of larger cloud droplets or ice crystals, which can then lead to increased precipitation. Cloud seeding agents. The most commonly used cloud seeding agents are silver iodide, potassium iodide, and dry ice, frozen carbon dioxide. Silver iodide and potassium iodide are used due to their crystalline structure, which closely resembles that of ice. This similarity makes it easier for water vapor to condense onto the introduced particles, promoting ice crystal formation in the cloud. Dry ice, on the other hand, is used primarily for its extremely low temperature, which can cause supercooled water droplets in the cloud to freeze upon contact. Methods of dispersal. There are several methods to disperse cloud seeding agents into the atmosphere. One common method is aerial seeding, which involves releasing the seeding agents from an aircraft, either through flares or directly spreading the substance. Another method is ground-based seeding, which involves the use of generators or rocket launchers to release the seeding agents into the atmosphere. The choice of method depends on factors such as the type of cloud, the altitude of the cloud base, and the desired effect of the seeding. Types of cloud seeding. There are two primary types of cloud seeding: static and dynamic. Static cloud seeding targets existing clouds, introducing seeding agents to promote the growth of ice crystals or droplets within the cloud, which can then lead to increased precipitation. Dynamic cloud seeding, on the other hand, aims to enhance the vertical development of clouds, causing them to grow taller and promoting the formation of precipitation through increased updrafts and overall cloud development. Effectiveness and limitations. The effectiveness of cloud seeding remains a subject of debate among scientists and meteorologists. While some studies have reported positive results, with modest increases in rainfall, others have found little to no significant impact on precipitation. Factors that can influence the effectiveness of cloud seeding include the type of cloud, the seeding agent used, and the meteorological conditions at the time of seeding. Additionally, cloud seeding cannot create rain in areas where there is no existing moisture in the atmosphere, as it relies on the presence of clouds and water vapor to function. Environmental and ethical concerns. Some concerns have been raised regarding the potential environmental impact of cloud seeding, such as the potential for silver iodide to accumulate in soil and water sources. However, most studies have found that the concentrations of silver iodide used in cloud seeding are well below levels that would pose a risk to the environment or human health. There are also ethical considerations around the use of weather modification techniques, such as the potential for unequal distribution of resources and the possible unintended consequences on regional or global climate patterns. In summary, cloud seeding is a technique used to encourage rainfall by dispersing substances into the atmosphere to stimulate cloud formation and growth. It involves the use of cloud seeding agents, various methods of dispersal, and different types of cloud seeding strategies. The effectiveness of cloud seeding remains a topic of debate, and there are environmental and ethical concerns associated with its use. Cloud cover, an important meteorological parameter, is the fraction of the sky obscured by clouds when observed from a particular location. It is an essential factor in weather forecasting, climate modeling, and understanding the Earth's radiation budget. Cloud cover is typically measured in units called octas, which divide the sky into 8 equal parts. Concept of octas. Octas are a unit of measurement that provide a simple way to express the extent of cloud cover in the sky. Each octa represents 1/8, 12.5% of the total sky area. Meteorologists use octas to quantify the amount of clouds visible in the sky at a given time, with the scale ranging from 0 octas, completely clear sky, to 8 octas, completely overcast sky. Observing cloud cover. Cloud cover is often assessed visually by trained weather observers or meteorologists who examine the sky and estimate the fraction obscured by clouds in terms of octas. Observers use various reference points and angles to divide the sky into 8 equal sections, and then assign a cloud cover value based on the number of sections that are filled with clouds. In some cases, automated instruments, such as sky cameras or kilometers, are used to determine cloud cover more objectively and with greater precision. Cloud cover and weather forecasting. Cloud cover is a crucial factor in weather forecasting, as it influences various aspects of the atmosphere, such as temperature, precipitation, and solar radiation. For example, a high amount of cloud cover can lead to cooler daytime temperatures by reflecting sunlight back into space, while low cloud cover can result in warmer temperatures due to increased solar radiation reaching the Earth's surface. Cloud cover also plays a role in predicting the likelihood of precipitation, as a higher cloud cover generally indicates a higher chance of rain or snow. Cloud cover and climate modeling. In climate modeling, cloud cover is an essential parameter for understanding the Earth's radiation budget and energy balance. Clouds can have both a cooling effect by reflecting incoming solar radiation and a warming effect by trapping outgoing long-wave radiation. Accurately accounting for cloud cover in climate models is critical to predicting how the Earth's climate will respond to changes in atmospheric composition, such as increasing greenhouse gas concentrations. Variability in cloud cover. Cloud cover can vary significantly over time and space due to factors such as atmospheric circulation patterns, weather systems, and topography. Some regions, such as coastal areas and mountain ranges, tend to have higher average cloud cover due to their unique meteorological conditions. Additionally, cloud cover can vary on diurnal, seasonal, and interannual timescales due to changes in weather patterns and atmospheric dynamics. In summary, cloud cover is measured in octas, which divide the sky into 8 equal parts, providing a simple way to express the extent of cloud cover. Octas are used by meteorologists and climate scientists to observe and predict weather patterns, understand the Earth's radiation budget, and model climate systems. Cloud cover varies across time and space due to a range of meteorological factors, and its accurate measurement and representation are crucial for understanding the Earth's weather and climate. The World Meteorological Organization, WMO, an intergovernmental organization responsible for coordinating global weather and climate activities, maintains the International Cloud Atlas. The atlas serves as the authoritative reference for the identification and classification of clouds, providing meteorologists, climate scientists, and cloud enthusiasts with a standardized system for describing and understanding cloud formations. History. The International Cloud Atlas has its origins in the late 19th century when a group of meteorologists, led by Ralph Abercrombie and Hildebrandsson, started developing a systematic classification of clouds. The first edition of the International Cloud Atlas was published in 1896, and since then, it has undergone several revisions to accommodate advances in cloud science and the incorporation of satellite-based observations. The most recent edition, published in 2017, is available in both print and digital formats, with the latter providing enhanced accessibility and interactivity. Classification system. The International Cloud Atlas uses a hierarchical classification system based on the cloud's appearance, altitude, and physical properties. The atlas recognizes 10 basic cloud genera, which are the primary categories of clouds: cirrus, cirrocumulus, cirrostratus, altocumulus, altostratus, nimbostratus, stratocumulus, stratus, cumulus, cumulonimbus. These genera are further divided into species, which describe the cloud's internal structure, shape, or arrangement. Additionally, varieties are used to indicate the cloud's transparency, arrangement, and the presence of any accessory clouds or supplementary features. Cloud identification. The International Cloud Atlas provides detailed descriptions, illustrations, and photographs of each cloud type to assist with identification. Users can consult the atlas to distinguish between different cloud formations based on factors such as their shape, texture, color, and the presence of any unique features. The atlas also provides guidance on identifying cloud formations from satellite imagery, which has become increasingly important in modern meteorology. Educational and scientific value. The International Cloud Atlas is not only a practical tool for meteorologists and climate scientists, but also serves as an educational resource for students, teachers, and the general public interested in cloud formations and the Earth's atmosphere. By providing a standardized system for describing clouds, the atlas promotes consistency in the communication of cloud observations and supports the advancement of cloud science. Applications. Accurate cloud identification and classification using the International Cloud Atlas are essential for various applications, including weather forecasting, climate modeling, aviation, and environmental monitoring. For example, Understanding cloud types can help forecasters predict the likelihood of precipitation or estimate the potential for severe weather events. In climate modeling, accurate representation of clouds is crucial for understanding their role in the Earth's radiation budget and predicting future climate changes. Clouds play a crucial role in regulating the Earth's temperature and energy balance by influencing both the amount of incoming solar radiation and the amount of outgoing long-wave radiation. They can have both a cooling effect by reflecting sunlight back into space and a warming effect by trapping heat like a blanket. The overall impact of clouds on the Earth's climate depends on a complex interplay of their properties, such as altitude, thickness, and composition, as well as the balance between their cooling and warming effects. Cooling effect, albedo. Clouds can have a cooling effect on the Earth's surface by reflecting a portion of the incoming solar radiation back into space. This phenomenon is known as the cloud albedo effect. Albedo is a measure of the reflectivity of a surface, and clouds, particularly those that are thick and bright, such as cumulus and stratocumulus clouds, have a high albedo. By reflecting sunlight, these clouds reduce the amount of solar energy absorbed by the Earth's surface and atmosphere, leading to a cooling effect. Warming effect, greenhouse effect. Clouds can also have a warming effect on the Earth's surface by trapping outgoing long-wave radiation, similar to how a blanket traps heat. This phenomenon is known as the cloud greenhouse effect. When the Earth's surface and atmosphere emit long-wave radiation, certain components of the clouds, such as water droplets and ice crystals, can absorb this energy and then re-emit it in all directions, including back towards the Earth's surface. This process effectively traps heat in the lower atmosphere, resulting in a warming effect. Clouds that are higher in altitude and composed primarily of ice crystals, such as cirrus clouds, are particularly effective at trapping heat. Balancing cooling and warming effects. The overall impact of clouds on the Earth's climate depends on the balance between their cooling and warming effects. Factors that influence this balance include cloud type, altitude, thickness, and the size and composition of cloud particles. Low-level clouds, which are generally thicker and more reflective, tend to have a net cooling effect, while high-level clouds, which are thinner and more effective at trapping heat, tend to have a net warming effect. Additionally, the balance between the cooling and warming effects of clouds can be influenced by the time of day, with the cooling effect being more pronounced during daylight hours when solar radiation is stronger, and the warming effect being more pronounced at night when outgoing long-wave radiation is the dominant form of energy transfer. Climate feedbacks and sensitivity. The complex interplay between the cooling and warming effects of clouds represents an important climate feedback mechanism, influencing the Earth's sensitivity to changes in atmospheric composition, such as increasing greenhouse gas concentrations. Accurately representing clouds and their impacts in climate models is critical for understanding how the Earth's climate will respond to human-induced changes and for predicting future climate scenarios. As you continue to breathe deeply and slowly, allow your thoughts to drift back to the clouds we've been exploring. Picture the soft, gentle clouds passing by, creating a soothing atmosphere of calm and tranquility. Feel the comforting embrace of their cool shadows and the gentle warmth of the sun peeking through their edges. Let the ethereal beauty of these clouds be a reminder of the serenity that exists within you. With every exhalation, imagine yourself becoming lighter and more relaxed, like a delicate cloud floating effortlessly in the vast sky. Your body begins to feel weightless as your mind becomes more and more at ease. The soothing colors and shapes of the clouds blend together, creating a nurturing and peaceful environment for you to drift into a deep, restorative sleep. As the clouds slowly dissolve into the background, so do your thoughts, worries, and tensions of the day. The sky gradually transforms into a canvas of velvety darkness, sprinkled with the twinkling of distant stars. The night sky embraces you with its gentle, protective energy, inviting you to surrender to the world of dreams. Now, let yourself be cradled by the tender embrace of the night as you drift deeper and deeper into a state of profound relaxation and rest. Feel the gentle whispers of the wind and the soft touch of the clouds lulling you to sleep, knowing that you are safe, supported, and at peace. Good night, and may your dreams be filled with the boundless beauty of the clouds and the endless serenity of the sky. Sleep well and awaken refreshed and renewed, ready to embrace the light of a brand new day.